Previously, we determined that we wanted to add together a finite number of areas of rectangles in order to solve the area under a curve problem. So let's discuss some notation related to sums, and we're going to look at sigma notation here. So our sigma notation is the Greek letter sigma. So we have our Greek letter sigma here. And below that, we'll write k equals 1 to say that we start at index 1 all the way up to n of some a sub k. And what does this mean? Well, the sigma notation means that we take our formula on the first index, so a sub 1, and then we're going to add, and then we keep going as we run through all of the indices here. So a sub 2 plus a sub 3 until we get to a sub n here. And so this right here is our sigma notation where we have the Greek letter sigma. Again, down below we have the index where we begin. The n is in the place where we have the index that we end with. And this a sub k is just the formula for this particular sum. This is what we add at each step. So let's do some examples so that we can wrap our heads around what's going on here. So some examples, part 1. So for example, part 1, part A, what if we had the sum from k equals 1 to 4 of k? Well, all right, we replace every k in this formula with our index. So we have k equals 1 for the first one, and then we add the next one. So we just run through our indices. We add 1, and then we have 2, then 3, and then all the way up until 4. So this just means the sum of the first 4 integers, which is 10. Let's see if we can try something slightly different. What if I had the sum from k equals 1 to 5 of k squared? Well, our first thing would be 1 squared. Our second would be 2 squared plus 3 squared plus 4 squared plus 5 squared. And what is that? 1 plus 4 plus 9 plus 16 plus 25 is 55. Let's try one more just to make sure we see what's going on here. We don't have to start at k equals 1. We can pick any index to start with, but these are integers. So let's go with k equals 3 up until 6. And now let's change up our function a bit. What if we did k squared over k minus 1? Well, this would be, we start our first index here, which is 3. So 3 squared over 3 minus 1, right? All we're doing is everywhere we see a k, we replace it with our index. And then we add, right? Our summation says we add each of these terms. We do the next one. Well, the next one would be 4. And we just keep going until we reach our top integer here. And then you just determine what those fractions are, and you can add those up. But I just wanted to show that how we read this sigma notation and how that turns into a sum. All right. Let's do some examples. Part 2 now. Let's express (1 plus 3 plus 5 plus 7 plus 9) in sigma notation. And for part A here, we're going to do starting at k equals 0. Now, what do we notice? First off, there are 5 terms here. So we need to have 5 terms. If we start at k equals 0, this means that we run all the way up through 4, right? 0, 1, 2, 3, 4 is 5 terms. And then we need some formula that will turn this k equals 0 into 1, k equals 1 into 3, k equals 2 into 5, and so on. Notice that as k increases by 1 each time, this value increases by 2 each time. So that should tell us our slope should be 2. So we get 2k, and then we have plus or minus something which we should determine by just plugging in k equals 0. If we plug in k equals 0 here, 2 times k is 0. So we would have to add 1 to get this first term. Now let's actually do that here. If we plug in k equals 0, we get 1. If we plug in k equals 1, we get 2 times 1 plus 1 is 3. K equals 2, we get 4 plus 1 is 5. K equals 3, we get 6 plus 1 is 7. And k equals 4, we get 8 plus 1 is 9. And in fact, we were right then. That this is the sigma notation representation of 1 plus 3 plus 5 plus 7 plus 9, starting at k equals 0. Let's do the same thing, but start at k equals 1 now. So we get k equals 1 to 5 now, because we need 5 terms. 2k, and now if we do 2k, 2 times 1 here, we'd be at 2, so we would need to subtract 1 to get to 1. And if you plug all of this in, you will see that you again get 1 plus 3 plus 5 plus 7 plus 9. And for part C, real quick, what if we started at k equals negative 5? We don't even need to start at a positive integer here. K equals negative 5, that runs up until n equal to negative 1. So this will be 2k plus, and through a little bit of observation, we see that this is plus 11. We plug in negative 5. 2 times negative 5 is negative 10, plus 11 is 1. 2 times negative 4 is next, so negative 8 plus 11 is 3, and so on. Oh, sorry. Plus 9 at the end. All right, and we will end the first video there.